Okay, good morning. So today we are given one combined solution for AX equals B, where A is a matrix of coefficients and B is a matrix of given constants. And we want to solve it with another way or method other than the Gauss-Jordan elimination method that we seen before. We will talk about some decomposition, which is called the LU decomposition, that is of order of n cubed, like the Gauss-Jordan elimination. But the benefit of this method is that we can use it for more than one B, and when we use it for more than one B, the B is the given constant. It is cheaper in terms of computational cost, and that's what we get from this method. Sorry. So again, if we have only one vector of B, this method is computationally equivalent to the Gauss elimination. But when we have more than one B, it is not equivalent. It's much more better. And again, we avoid solving the equation with finding a minus one and then multiplying by it, because the LU decomposition and the Gauss elimination method are much more better in terms of errors. Okay, the a minus one contains more errors than when we multiply by x, we accumulate these errors. Okay, so these ways are better. And the first thing I want to convince you in it that A, I can find for it and in the LU decomposition, we're talking about square matrices. A is a square matrix, and I want to convince you that I can decompose A to a multiplication between two matrices, L and U, such that the U is an upper triangular matrix, and the L is a lower triangular matrix. That's why it is called L, lower, and called U, upper. Okay, I want to convince you that we can do this. Yeah.
And this method is going to be computationally cheaper than doing Gauss-Jordan elimination on a whole array of B vectors?
The decomposition itself is no. It's not. It's also of order n cubed. Okay? But after we make the decomposition, the usage of it is much better than the usage. It's much better if we want to solve for more than one. Okay. And I mean by that many B's, not only one B.
Not two.
Many B's, yes.
Yeah.
Okay. So I want to convince you in this, and you know that always you can use Gauss elimination. You know, always you can use Gauss elimination in order to bring A by Gauss elimination, in order to bring A to an upper triangular matrix, which is the reduced row echelon form. Okay? And this elimination contains only the process of changing Ri to ARI plus B. I can make this A. But let's take A, which is not 0, plus B, Rj, where the J is smaller than I, I make the elimination only using this row and the rows before. This row and the rows before. Okay. And suppose for now that we don't use swaps. Okay, suppose that the pivots are good. Okay, we can do this elimination without swapping the rows. So, you know, I want to convince you that we can get to this. That's the target for me in this explanation. So if I can make the elimination without swaps, each one of these operations is equivalent to multiplying by a lower triangular matrix. Example. If I take this matrix and move it or transform it to another matrix, which is the same matrix, but changing, for example, R2 to 3R2 minus 5R1. Okay? This transformation is equivalent to taking this matrix and multiplying it by 1 here, 0 here, 0 here, 0 here, 0 here, and the R1 remains the same, and I take 3 minus 5. Okay. Check it. Okay. So this goes with this. This remains the same. This multiplies this. This one remains the same. This multiplies this. This one remains the same. But now, this multiplying this is minus 5 this plus 3 this. So I've taken minus 5 this plus 3 this, and I replace this by 8. So that is replacing R2 by 3R2 minus 5R1. Okay. Any question? And you know that I can do the elimination such that this A always is 1. Again, suppose there is no swap. This A always 1, so this will be always 1. The diagonal. Okay? And if I do this elimination by many operations like this, and these operations are the operations of the algorithm of Gauss elimination, which takes rows and subtract other rows that are above. And it starts with the second row, and then the third row, and fourth. So I can write if A is this, so I take A and make the first operation, and then I make the second operation, and then the third operation, and after that I get to the U. Then these operations, which are lower triangular matrices, are L minus 1, and I can take L. I can take the inverse of this, and this is L. And of course, lastly is the inversion of lower triangular matrix is a lower triangular matrix. The answer is yes. And each matrix of these, is invertible. You can know. This transformation is invertible, so each matrix is invertible, and it is also lower inversion, a lower triangular matrix. So I think now you are convinced that I can say that this A is equal to some, always to some lower triangular matrix multiplied by upper triangular matrix. And how do I find this? basically it's by Gauss elimination. We will give equations for that, but basically we do this elimination. But what if we have swaps? We also can do the same thing, but let's think about it in another way. If I have swaps, so I start my elimination, I started, do things, and I discover here that it's better for me to change the pivot and swap, for example, the 7th row with the 2nd row. Okay. And suppose that here I also find out that I have to change the pivot and swap 4 with 5. Okay. So what can I do with this? The answer is, if I do this change, so I start the elimination, see, I start the elimination and go like this. If I make an operation, and after that an operation, and after that an operation, this is the order. So I can say equivalent of this process, I can make these changes or swap at the beginning, which means I change and swap, set the 2nd with 7, and I can change the 4 to the 5th. And after that, after I make all the changes I had to do, after that I make the elimination.
How do we know that's good?
It is not the same one and M2 and M3, but it will give me the same at the end. Okay, I think you are convinced that this is true. It is not the same M1 and M2 and M3, but if I do the elimination, when I change these, so here instead of making M3, for example, I will do the same for M7, not M3. Okay.
What I'm confused about is why would the same pivots that we found to be useful with those M's would still reduce the errors for different operations?
Because these are the rows that you chose to be pivots. That's it. When you make a general permutation using this, it's all you have decided or determined by this which row will be the pivot. Yes.
Can you explain why we are supposed to be convinced that LU are triangular or metric?
The M's are not.
No, and you are.
Yeah, I'm sorry. These ones.
How we were supposed to understand that.
Yeah. Again, you already know that you can make elimination to get to an upper triangular matrix. That's something that you know from a course before or from this book. Okay. You start with the first row, don't change anything with it. You go to the 2nd row and nullify the first element. How to nullify it? Take the 2nd row, replace it by the 2nd row minus A21 divided by A11 multiplied by the first row. Okay. And continue the elimination. That's something that we know. Except that if we get to a pivot, you see here that I divided by A11. But what if the A11 is 0? So I change, I swap the rows. Okay. So I know that this is something that I can make. And if this is the case, my elimination will be that PA equals LU. Okay. That's my elimination. That's my decomposition. Okay. So any A, I can bring it now, not to LU, but to a swapping matrix multiplied by L. Okay. Questions on this? And the question, yeah,
How will the swapping matrix look?
yes, I will explain. Oh, so now the question is, how to find the L matrix and how to find the U matrix. We know that there are matrices like this, and again, basically it's the elimination method and keeping in mind these operations, but we can do much better than only saying this. But as he asked, what is the P? So if I want to change or to swap between two rows, I and J, the P that will multiply the A is ones on the column, except the I and J, there will be zeros, and the element ij and ji, they both equal. Okay, that's how I change rows. That's the swapping between 1 and 2, between I and j, and you know that swapping are not commutative, yes? So if I swap 1 and 2, and after that 2 and 3, it's not like swapping 1 and 3 and then 1 and 2. Yeah.
Something.
So P12, P23 doesn't equal to P23, P12. Okay. And what is the determinant of P like this? The Pij, what is the determinant? It's the determinant. Huh? No.
Oh,
No.
-1.
Minus 1. So take the simplest one, 0, 1, 1, 0, and 1's here. Okay. So the determinant is -1. So a general swapping, general bunch of swappings has a determinant of -1 or +1, depending on
The times of.
yes, is it even or odd, and we call this the parity of the permutation, of the overall permutation of the rows. Okay. So let's always when you have some recipe of a decomposition, in order for you to find that decomposition or to find an algorithm to find the decomposition, try it with matrices 3 and 3 and matrices 4 and 4. So let's try it with matrices 3 and 3. And I want now to find what is the L and U. Okay. After I found the L and U, what will I do? Okay. Suppose that you have the L and U. What will you do if you have the L and U?
Multiply and compare to the metric.
If I have the L and U, if I make the decomposition and I have the L and U, and I want to solve AX, which is LUX equals B, if I know what is L and U, I can solve for Y, Ly equals B, and find Y. And after that, I will solve Ux equals 1 and find X. And why it is easy? Because Ly equals B, this is a lower triangular matrix. So my way of solving this is not by backward substitution, but by forward substitution. The y1 equals b1, for example. And then I have y2 equals b2 minus that y1 multiplied by L12, which is the L12 from here. Okay. So if I get this L and U, I will solve the equation, the set of equations L y equals b and find y. And after that, I will solve y equals ux. This I solve it y backwards. Okay. So for now, I want to build an algorithm to find this u and l. Okay. So again, I try with three 3 times 3 matrices. And let's go. Sorry. Yeah. So if I take the 2 matrices to be a general lower triangular matrix and general upper triangular matrix, and take these to be L11, L22, and L33, then I will have 6 plus 6 variables, 12 variables, for how many equations? 9 equations. Yes. So there is a redundancy. Okay. If there is a solution, it might be that there are infinite solutions. Okay. Again, I want to find. I know what is the matrix A, that I know, and I want to find L and U, that the multiplication of them gives A, where L is lower triangular matrix and U is upper triangular matrix. And I suppose L to be like this, suppose U to be like this, and if I suppose L11, L2 to L23 general variables, I will have 12 variables here in order to solve 9 equations. The A11 should be equal to this, and this should be. So because of this redundancy, I lower the number of variables by fixing 3 of them. And I always fix the L11 and L22 and L33.
And that leaves us with the right amount of variables.
Hmm?
And that leaves us with the right amount of variables.
And I know I can do this also because I know that I can do the Gauss elimination with only A equals 1. Always. Okay. And anyway, I try. Anyway. And when I write down this, I see that I can solve the equation with the first column, and then the second column, and then the third column. How do I do this? Look at the first column. U11 equals A11. Here I know what is the U11. After that, again, I will solve for the columns. What I mean for the columns, I mean that I will find this column and this column in the first step. Okay. So I already know that this is 111. The LII, I know what it is. And I know that these are zeros and these are zeros. Okay. So using this column, I will find this and this. How do I do this? U11 equals A11. Okay. Now I know what is U11. L21 U11 equals A21. So the L21 is A21 divided by U11. Okay. Now,
The other way around.
Huh?
You're trying to find U, right?
I want to find U and L. Both of them.
Oh, you want both?
Okay. So for U, I have to find only U11 because these are zeros. And for L, I have to find only this because this one I know. Okay. So the L21 is A21 divided by U11 that I found, and L31 equals A31 divided by U11 that I found. And that's it. I found these two columns from each column.
Without doing any elimination.
Yes. But this is the elimination. You will see that.
No, it's equivalent, but it's
Yeah.
different.
So here it gets bigger and bigger. Yeah. Now, the second row, I will find these numbers using the second column. I already know what is U11, L21, L31. So L21, this I know, and L31 I know. Okay. Now the U12 equals A12. Now I know what is U12, and I know what is L21 from the step before. So the U22 equals A22 minus this. And now I know what is U22. And I know what is U12. And I don't know what is L31. So I will know what is L32. Okay? Because this equals A32. So I found this column. And after that, I will find the third column. Okay. So that's the spirit, and that's how we know what is the solution, and we can now write general equations. We can take the general matrix L to be like this, and the general with n times n, and the general U n times n, and multiply them and type or write down that Aij should be the multiplication between them. And if Aij equals the multiplication between them, let's write what is Aij. It is the sum over k from 1 to n of what? I'm doing this because you say that you didn't understand so much in the lecture. So I do it now. I'm not supposed to do this. The Aij equals what? Lij, it's a multiplication between two matrices. Lij u, I'm sorry, k,
Oh.
ukj. Now I know something. What I know? I suppose something. Here what I assume. What do I know? I know that for k that it is bigger than I, this equals 0. And also for k which is smaller than j. Okay. K goes from 1 to n to I. But let's say to I minus 1. Lik u k j. And the ith one. What is the ith one? It is Lii multiplied by uij. But Lii is what?
1.
1. It is 1. Okay. So that's the set of equations I will solve for every I and j, but I know that I can solve for them. I know from my experience that I can solve them column by column. So I built an algorithm for that, and start with the first column and find the u's corresponding to that column and the l's corresponding to that column, and then go to the second column. I know that I can solve the equation. I wrote them down. I try and we'll find yes.
Said u is 0 when k is smaller than j. Right?
U is 0 when
K is
k
smaller than j.
is bigger than j. Yes.
Well, it depends on your definition. Question is, shouldn't like the sum include two boundaries? Like, shouldn't the sum be from j to I minus one?
No, I choose to write it like this, and then I will show you that I can solve it for the same j I can and run over the I. Okay. So again, what is the solution of this? I'm not so I'm not well ordered here because I do all the calculations. So that these are the U's and these are the L's. Okay. So how to find the matrix L and the matrix U? We make in each step calculations also for U and calculations also for L. In each step, I find the U's and the L's for the corresponding column. So I start with the first column, and in the first column, in the matrix U, I only have what? U11 equals A11. So here, when you see, so I is 1, when you see that there is a summation from 1 to 0, it means don't take this. So U11 equals A11, and I'm still in the first column. I finished my job in the U's, because in the first column in the U's, I have only U11, and I go to the L's. In the L's, I have the L11 is 1, and after that, I have the L21, the L31, the L41. So the Li1 is 1 divided by U11, and again, because I'm talking about the first step where j is 1, it's only the AI1 divided by U. Okay. So you can see that this equation comes from here. Okay. And also this equation comes from there. But this ordering of the equations and making column by column make us solve for the U's and the L's depending on previous U's and L's that we solved. Okay. So the L's are this, and I found all the L's that you see here and the U's that you see here are found before. In the previous column or in this column, for example, the U's, I found them first, and then I found the L's. And then I find the U's of the next column depending on the L's of the previous columns. Okay. Any questions? That's our algorithm for finding L and U, and it's called Crowd's algorithm. Okay. So now let's see if we want to see examples. Oh, so in order to complete the picture for you, we talked about 3 times 3 matrices and degrees of freedom. If it's n times n matrices, so if this is a lower triangular matrix with general numbers on the diagonal, how many degrees of freedom do I have for it? So it's this triangular plus this column. How many elements in this diagonal and in this triangular? It is n squared minus n, so that is without the diagonal, divided by 2, plus the diagonal. So if L is a general lower triangular matrix, this is the number of the degree of freedom, and also for U, the same.
It's just n squared plus n.
And then the sum of them is n squared plus n, and therefore, if I want to find L and U that that look like this, and the multiplication of them equals 8, I have n squared plus n variables with n squared equation. So again, I have a redundancy of n numbers, and I can fix the diagonal of L to be ones. Okay. And again, I show you that the U and the L are, if we do the Gauss elimination, the U and the L are gotten from that elimination. Okay. This L will be the A21 that was before divided by the A11, and this will use the primes. You remember the primes? The primes, I get them after one step of Gauss eliminations, and the double primes, I get them after the second step of Gauss eliminations. Okay. Okay, so let's talk about this and see a simple example. Yes. Okay, so again, that's the algorithm for finding L and U. If we have the L and U, what do? We solve the equation Ly equals V by forward substitution. So this is the forward substitution, and divided by Lii is divided by 1 here. Okay. So in this substitution, we go from the first element, from the first y to the second, third. And after we find the vector y, we solve ux equals y. So ux equals y that we applied already. And we use backward substitution because the U is an upper triangular matrix. So we start with the last one, and we know that UNN XN equals YN. So the XN will be YN divided by UNN. And after that, we take the previous equation, which has only XN minus 1 and XN. We know what is XN already because we found it. So it's the backward substitution recursively. And let's see an example. Suppose this is the matrix A, and its decomposition looks like this. So if the decomposition looks like this, we solve this Z is Y. We have Ly equals B, that is the L. So Ly equals B, and we go with forward substitution. So Y1 equals 7, and Y2 equals 11 minus 2 multiplied by 7. So it is minus 3. And Y3 equals 31 minus 3 multiplied by 7 minus 1 multiplied by Y2, which is minus 3. And then we find this Y3. And Y4 also we find it the same way. It's 15 minus 7 minus 1 multiplied by minus 3 minus 1 multiplied by 13. That's and after we found this Y vector, we solve for U multiplied by X equals this Y. So it is the backward substitution now. So 12x4 equals 18. Okay, and we substitute this x4 and find the x3 and etc. So again, what's about pivoting? Again, if we want to change roles, and you know that changing roles here, it's either because the element itself is 0 or because it is too small. if we do this pivoting, the way that we will get the LU decomposition is an LU decomposition not for A, but for A with swapping between the rows. And there is a function in Python, or in SciPy, that gives you this. If you give the function the matrix A, it will give back for you three matrices, P and L and U. And the meaning of that is this, where the P is a matrix of swapping, or permutation matrix. That's what it, that's the reason for it to be called P, permutation. Okay?
It finds the P that fix only the zeros or also the small numbers,
This P, again,
like this function.
Yeah.
This function it finds the P that will fix the zeros that will be
yes,
the,
the P
and
that,
also the really small values. It will move them not beyond the.
that's a good question. It is, I think yes, I think yes. I don't know exactly, honestly, but I think yes. I think it makes the best swappings that it can do numerically. Yeah. Analytically, there is no difference between swappings. If there is a set of swappings and another set of swappings, but both of them give you LU decomposition, so it's all good. But numerically, there's difference. And I think that it makes the best one numerically, and we learn how to do that numerically. We always look in the next in the next step. We do what's called partial pivoting, in which we search the maximal value. Yes, you can go back to the previous recitation and see that we take the maximal value of the column. So we take the maximal value on the column to be a pivot, and then make this swapping between the rows. Okay. Again, how do we do this? We start with the rows and search the biggest or the largest in terms of in magnitude. Yeah, the largest I1. And when I find the largest I1, I swap the row I with the row 1 and start the first step of elimination. After that, when I go to the second step of elimination, I search in the second column the biggest number, yeah, the largest number, and make the swap, and then do the elimination. Okay.
Mohammed,
Yeah.
when we choose the biggest number, isn't there potentially an issue if the number is extremely big? If there's like one element in the matrix that's like many orders of magnitude bigger than all the other ones?
Yes, but that's the best I can do. Yeah, there is a problem, but that's the best I can.
There's like, that's the trade-off.
Yeah, if you have a matrix of many numbers and only one number which is 10 to the 9 times of these numbers, there is a problem.
All right.
Okay. So what about the determinant? I remind you that the P has, if you get this P, L, and U, then you will know the determinant of A immediately. Why? Because the P has a determinant of plus minus 1. You know that from the parity of the permutations, and the U and the L will have determinants that are the multiplication or the product of their diagonals, and the diagonal of L is all ones. It's full of ones, so its determinant is 1, and the determinant of A is left to be plus or minus the multiplication of the U's on the diagonal. Okay. So after you make the decomposition, the determinant so easy. And this is something that we always want to do, and maybe you will feel not good with it, but it is something that we have to do when we do anything numerically. We have to check our error. Okay. So suppose now, forget what we've done for now, and suppose that in order to solve the equations, I found a minus 1. Suppose that. And then I took a minus 1 multiplied by b and tell you that the answer is b. Okay. Don't forget that when I found a minus 1, it is not really a minus 1. It is a minus 1 with some error. It is error. Or noise. No, it's a minus 1 with error. Okay, so it's not really a minus 1. If it's exactly a minus 1, our solution doesn't have any error. Except that the multiplication of a minus 1 with b has itself round of error. Okay. So this is a minus 1 with error. This error can be 0 or not. When we multiply by b, there will be an error in b. So suppose that we have a solution after we do this. So I will say that suppose that my numerical method told me that the solution is x. This x, which is the solution of mine, which is the result of my numerical method, is not the real x. It is the real x with an error that I don't know what it is. Okay, so I've done something numerically. I found an answer to the question, ax equals b, found x, but it's not the real. It's the x with some error that I don't know. And I somehow want this error to be small. If this is the situation, then if we multiply this by a minus 1, that we think it is a, which is not the real a. Okay, so let's call it bar. It will be a. So it will be ax plus a delta. And again, if I do this multiplication, somehow I have error. So it's supposed to be, so this is somehow delta in b, and this is b. Again, if my calculation is good, if it's exact, if my multiplication here is exact, I will have the p. Therefore, the delta x is a minus 1, a x prime minus b. Again, you can get this from there immediately. But again, when we do the calculation, this is not exactly b. Therefore, this will be not 0. Okay. And why do I write it like this? Because now, after I found some solution, I can know somehow what is the error in this solution. Okay, by taking it, multiply it by A, subtracting from that B, multiplying that by A minus 1 that I found. I told you, suppose that we found A minus 1, and then hope that this is small. Okay. After I found this delta x, which is from these, I don't take x, I take the solution to be x prime minus this delta. And again, if this is an analytic thing that is written here, and I tell you that x prime is x plus delta x, and do this calculation, you should get here to x. Yes? But again, I make here numerical calculation based on previous numerical calculations. So I get another x, which I hope that it's closer to the x. Okay. So again, and I hope that if I make some iterations, I get closer and closer to the exact answer. So again, there is a solution of the problem. Numerically, I got some solution. So I take that solution, multiply it by A, subtract B, get this, multiply it by A minus 1. I hope to get to delta x, to the real delta x that was added to x in my approximate solution. If it's the same delta x, the subtracting of them is x. But this will be not exactly the delta x. But if I subtract this minus this, I hope to get to some closer. Okay, and I call it x prime. And again, I can go again to my iteration, to the next iteration. Okay, so that's how we check our solution is stable or not. So, and this is important because of the next topic, which is differential equations. That's how we have. That's how you will find out if our equation or our solution of the equation is stable or not. So for now, you might feel this is redundant somehow, but it's important. Okay. Again, numerical calculations, you have to somehow measure your error, or at least know that you are converging to something. Okay. So let's now take a break and then go back to SVD. Okay. So now we'll talk about what's called SVD decomposition, but it's SVD only, without the word decomposition, because SVD is singular value decomposition. And this decomposition exists for every matrix. That's the nice thing. For every matrix, square matrix or not square matrix. And if it's square matrix, it can be singular and it can be not singular. We can find this decomposition. And this decomposition says that if A is an n times m matrix, we can write it as the multiplication between u n times n, w n times m, v transpose m times m. Where the u and the V are orthogonal matrices. And the W is a rectangular matrix. You see N times M, and also A is N times M. So a rectangular matrix, but it's diagonal. It's diagonal, rectangular matrix with non-negative values on its diagonal. We always can do this. So again, in this way, the N is smaller than M. This way of affecting the matrix. But if N is bigger than M, the way to affect the matrix is this. Okay. We always can do this. And the values, these values are called the singular values, okay, of the matrix A. And if we are talking about complex numbers or complex matrices, we also have a decomposition. The decomposition is U, W, V, where U and V are, and this V is V, where U and V are unitary, not orthogonal. Okay, more than wider than. Okay. Questions? Okay. So if you know that A is square, is a square matrix, and a diagonalizable matrix, you know already that you can write it like this. That's something new. Okay. Questions? Okay. So if you have this decomposition, I didn't tell you how to find it. So now, but if you have this decomposition and want to solve AX equal to B, how can you find it? So remember this. If you have this, how do you solve the AX equal to B? It is only A minus 1 multiplied by B. And what is A minus 1?
Transpose B minus 1 P.
It's the same P, but this is 2 minus 1 and P transpose. Okay.
I know is you swap P and the P transpose like
What?
A minus 1 in A minus 1, you swap P and P transpose like
Yes, but I make minus 1 to them, and the minus 1 is transposed, but it is orthogonal, so it is P also. Again, A minus 1 B is P lambda P transpose minus 1 B, which is P transpose minus 1, it is P. Lambda minus 1, P transpose minus 1, it is P transpose. P minus 1 is P. Okay. So that if A is diagonalizable. Now suppose this is a square matrix, this A, and this is a square matrix, of course, and this, and suppose that these non-negative numbers are all positive. If all of these are positive, what's the solution? If all of them are positive, so the determinant of A is not 0, because the determinant of A is the determinant of this multiplied by the determinant of this multiplied by this. So it's not 0, it's not singular. Okay. Again, suppose that A is square matrix, and suppose that W doesn't have zeros on the diagonal, so all of them are positive numbers. Then the determinant of A is the determinant of U multiplied by the determinant of W multiplied by the determinant of P, which is not zero. So it's not single. And the A minus 1 is what? The A minus 1 is
P minus one,
V.
P minus one, P.
W minus 1 U transpose.
What?
Because the U is orthogonal and the V is orthogonal. So U transpose equals U minus 1.
Oh,
Now suppose that the W here has 1 0. What do I do? If it has 1 0, I know that that A is singular already. Okay. If A is singular, what about this equation? What happens to it? What's the meaning of 0? If A is singular, do I have solutions here or what?
No, you have a single thing.
You either have infinite or zero, or
Huh?
infinite solution or zero.
Okay, that's good. So it might have no solution, and it might have one solution, and it might have infinite solution. Okay, I don't know. For example, here's a set of equations: 1, 5. Let's say 2, 5. X equals 2, 5. These are two equations of one variable. So that's the meaning of A be singular, yes? If A is singular, this means I'm sorry. If A is singular, this means that I have a more variables than I want. Yes. So that means that I got 11 more examples. Yes. So after elimination, I will get, for example, 1x plus 2y equals 3, and I will get that 0x plus 0y, this is after elimination, equals something. Okay, if that something is 0, there are infinite solutions. If that something is not 0, there is no solution. Okay. That's one thing to say. Another thing, if A is not a square matrix, and the number of variables is more than the number of equations. Okay, so n is less than n. What do I have then? This is my second example. If I have something like this, so it might have one solution. Here is it. And it might have, for example, 0 solution. Okay, it depends on the equations. Okay. But even though this doesn't have any solution, and this might not have any solution, I want somehow to find an x which is the closest x that can solve it in some manner. And I will choose my metric for that. Okay. Again, when I have something like this, which means, for example, that I have 1, 0 in W, there might be solutions and there might be no solution. and I will try to find the solutions. W is not invertible. I will try to find solutions, even though W is not invertible. In this way, how do I try to find solution? I avoid the last equation. Okay, I avoid it. I neglect it. And hope that if I neglect it somehow and find a solution, I hope that it's a solution. And if not, I hope that I can make it closer and closer to the closest x that can solve this equation, even though it's not solvable. Okay. For example, here I will search. Here I will search the x that makes if ax equals b. If I know that it doesn't have any solution, I will try find an x that makes this minimal, for example. Okay. So if there is a solution, I will find an x that gives me ax minus b. The norm of it is equal to 0. If there is no solution, I will try to find a solution like this that gets me minimum of that function. Okay. So let's go back to avoiding or neglecting the last equation. How do I neglect it? I try to find w minus 1, but I neglect that 0. That's it. Okay. So now suppose that w has, if w doesn't have any 0, that's the solution, and it's one solution. If w has a 0, it is not invertible, but I will define, and A is not invertible. I will define some matrix called A minus 1, but it's not an invertible matrix. I will define it to be the inverse of this, even though this doesn't have any inverse, but somehow in some way of thinking, the inverse of this, which is V multiplied by something multiplied by V transpose, and so multiplied by V transpose, and this is somehow the W minus 1. What is this W minus 1? It is W minus 1 avoiding dividing by 0. So for example, if I have a 0, I don't divide by it. If W is 540, the W minus 1 is 540. I avoid this 0. Yeah.
Is there something like a well-defined convergence radius for this thing? Or like it will converge up to a point? Or like, can you define how well this technique works for the general case?
I'm sure that the answer is yes, but I don't. But it's not a radius of convergence. It's something else. Something called, dependent on these singular values. But yes, the answer is yes, but not something that I know of. But I'm sure the answer is
More like
yes.
a plane of convergence.
Yeah.
There's a convergence space. That does not.
What do you mean by convergence?
No, like you'll get
Convergence?
the best point that.
Can I find the minimum here?
Yeah,
I can find a local minimum. Yeah.
yeah, but it'll be confined to a specific space that does not include the target value. But you'll find the closest point on that space.
Again, if there is a solution, I will get to that solution. But if there is not, if there is no solution of this, is there a minimal value of this and one vector that gets me to there? The answer is, I'm pretty sure that there is an answer of this, but there's more than one vector that gives me the same. Okay. But if I start with some vector, I will converge to one vector. Okay. So that's my one. That's it. And this is the analytical way. And numerically, not only zero numbers I avoided, but also very small numbers I avoided. How much small? Small relative to these numbers, to the maximal one of them. Okay. So I compare each number in this diagonal to the maximal number in this diagonal, which is 5 here, and check. For float storing, we will take this ratio to be 10 to the minus 7. If it's smaller than 10 to the minus 7, we take it to 0 or 10 to the minus 6. For example, if this is 10 to the minus 6, so compared to the 5, it is too small. If we store with a float way of storing, so I will take this also to be avoided, to be 0. So that's our way of using the SVD decomposition. Okay.
But how small does it need to be in order to live that?
Again, if this divided by the maximal value of this value is smaller than, let's say, 10 to the minus 6, I throw. And if I use double float, it's 10 to the minus 12, for example, or 13. It's your choice. Okay, and I will give you something to taste, at least. What are these singular values? These singular values are the roots of the eigenvalues of A transpose A. Okay, so if you, so we are finished. We are finished for now. I told you there's a SVD, singular value decomposition. It's like this. If you have the U, W, and V that make this, you can somehow find some semi inverse matrix of A using the semi-inverse matrix of W. But now I want to tell you what are these singular values for your knowledge. If you take the matrix, for any matrix A, you take A transpose A. For any real matrix, you take A transpose A. This is a symmetric. And because it is a symmetric, it is diagonalizable with non-negative eigenvalue. That's something that I hope that you have proved before, linear algebra. So it is diagonalizable, call it M, with lambda 1, lambda. Like this lambda. It is diagonalizable with sigma 1 squared up to sigma n squared. And this is n times m, n times m, m times m. Okay. Sorry. Now, if A is diagonalizable, A itself, if it's diagonalizable, so it has its own lambda. Yes. So what's what's the connection between this lambda and these singular values?
Well,
Some square root. So the determinant of this is the square of the determinant of this. So if we uh, make the same order, there is one correspondence between this column and this column, this diagonal and this diagonal, and we can relate each sigma to one of the lambdas and each lambda to one of the sigmas, and we have that lambda squared is equal to sigma to the fourth, and then lambda is equal to sigma. Okay. Again, these sigma, these are the eigenvalues of A transpose A, and the sigmas are the sigmas that are not. Okay. So how to find the matrix W? The answer is find the eigenvalues of A transpose A. Okay. I didn't prove for you that I can make this decomposition, but I'm adding some knowledge to it, okay, without proving the whole thing. So the first thing I tell you is you can calculate W by only finding the eigenvalues A transpose A. And the V also you can find it by only finding the eigenvectors corresponding to these eigenvalues. Okay, so the V is the matrix of the rows of the eigenvectors, the normalized eigenvector. Okay, and the U is more complicated. I will not explain about it, but it also uses things that you know, but uses branch meat, and I know that you don't like it. Let's see. And to remind you these things, let's take this matrix A and find for it at least the W and the V. Okay, so this matrix, you see that it's not invertible, it's singular, but calculate for it A transpose A and get this matrix M, and this matrix M, I'm sure that you are sure that has 0 eigenvalue. You know that because the A is singular, so M has to have at least one singular eigenvalue, which is 0. And how do we find the eigenvalues? We take the determinant of lambda I minus 10. So you have one lambda is 0 and 1 is 10. So the singular values, the sigmas, are the square root of these. The sigma 1 is the square root of 10, and the sigma 2 is the square root of 0. And then if we want to find the V, we will find the corresponding eigenvectors. And we know that the V is orthogonal, is an orthogonal matrix. So because of the 2 times 2 matrix, it's enough to find V1 and then to find V2 that is perpendicular to it. So to find V1, I go with the matrix multiplied by a vector equals the eigenvalue multiplied by the vector, and I will find the vector but not the vector, the normalized vector. After I find it, I normalize it. Okay, I don't forget to normalize it. And after and after I found this vector, I can do the same thing to find the zeroth vector, which satisfies this equals 0, because it's an eigenvalue of 0. But again, I know that the answer will be perpendicular to this p, so it is immediately this. Okay. I can guess it, not guess it, find it without make that calculation. So this is the p, and I'm not telling you the whole algorithm, but u1 is a multiplied by b1 divided by the w11, and after that, again, we make some Gram-Schmidt process, but again, because we know that the matrix is orthogonal, it's a 2 times 2 matrix, we find one vector in it, so the second vector is what? Is this, but here -1, 1.
Can you explain again how we find the V?
It's sorry, but I don't know that this is -1. It might be this -1 or this -1. So the process will fix or will determine that. Again, what's your question? How did I find the V? The V transpose is the matrix of the rows of the eigenvectors corresponding to the
How I am choosing the order of the matrix, which vector I should place in the first row and which vector I should place in the second row of the input. Like you chose in this example that the vector of the lambda equals 10 to be the inverse.
you can choose whatever you want.
But
If you choose lambda1 to be 10, then you have to find b1 to be corresponding to that lambda1. Okay, so if you put the 10,
yeah.
okay, that's one thing. The second, it is a convention that we take the bigger one to be the first, and the second one to be the second, and it's a good convention. Okay, any questions? Okay, so I uploaded for you something that you have to look into a little bit more deeply, but it finds the singular value decomposition, and it uses this function, which is a good function, you should know, that makes this comparison between the largest singular value to the smallest singular value of some matrix. Okay. So it's a function in SciPy again, but again, this code somehow implement the finding of this singular value decomposition. And
Will our homework be to implement this ourselves, or?
No. I've not uploaded the exercise yet, but it will be uploaded today. And the next recitation will be the last, as the man asked for. As he said, there will not be more, and we can make a review recitation, or not make that. It depends on you. So you will tell me if you want the week after.
Like the homework.
No, the homework will be uploaded today, and you will have today a homework, and the next week homework, and that's it. So that's it for today. Any questions? Oh, so see you next week.